Okay, so for parsing this, I think what I'm gonna do a Pratt style parser that has um, sort of a dispatch function that will use a table to call a function depending on the token. It's pretty straightforward, pretty reliable. So it's a parselet. That's what I call it some other times. Okay, and then we're gonna have so parselet can have either a prefix function and or a infix function. So let's see. So let's define those. Oops, sorry. Let's define those first. So it's going to generate an ASD node, whatever that is. We'll define it later. And then what's this? Just put a node, I guess. It's just gonna generate a node, and it will take the. I guess it'll just take the parse state. Let's see. So prefix key state is the argument. This one. I think I'm like sitting at a weird angle. Maybe that's why I'm hitting the wrong keys. Oh hey Yoey, good to see you. So we have an infix parselet. This one is a little bit more complicated. First off, we're gonna take the do we need that? We might need the parselet itself. So this guy, we might need that. So I'm just looking at one of my other parsers. Okay, so we have the parselet. Let's just pass it in for now. We can just remove it later if we don't need it. And then we have the prefix node. So we can have node like prefix. Actually, maybe I should just give this a better name. It's just not node. Oh. So prefix or like the left side. Maybe left is better. So like an infix part. So like a prefix parselet will parse something like token. And then some token that it's mapped to in the table, and this thing is only called when there's a left thing and then token, and it's called with both of these two, and then it can do stuff. So it's useful for then with some precedence rules. We can build up a pretty manageable parser with this. Hey, Badrol, good to see you too. Hope you're doing well. Okay, so anyhow, we're gonna have these two. Oops, this is incorrect. Infix parselets. First key state. It's the first argument. So we're gonna have the prefix and then the infix. And now we're gonna have the precedence here, or precedence. And I'm gonna copy paste some precedence rules from one of my projects called CO. And we're not gonna need. Actually, I'm not sure if we're gonna need infix operations. I think we'll need for the equal sign at least, but I'm just gonna toss these in for now. Toss them in here. And that's just whatever U8 is now. It really does the space requirements here like 0. So lowest assign, comma, or bitwise. Let's just keep these for now. surfer again from the CO project. So that's the precedence there. So now we're gonna, let's just make sure it didn't screw up. Oh, of course it did. What am I missing here? Oops. Gotta love C's weird ass syntax for function type types. Hey MDS. What is up? Okie doke. So now we're gonna put together a little table for our parselets. Again, I am looking at the parser derivative for CO. I'm gonna use whatever we need, but no more. So in CO, I actually generate this table I'm about to paste in here. In this case, we are not going to generate it because it's so simple, this language. We can just write it automatically. So what this does, and we call this parselet lowercase b. So this is the parselet table. It can't be called parselets. Let's see. We call other things like tab with tables. So let's just call this parse tab table. And then do we have a max token thing? We do have, that's called our token count. That's kind of weird. Just this. So all the other tokens are kind of called T. So this table is kind of key to this Pratt style parser thingy. It maps a token to one of these parselet structures, which has, you know, oh, these should be nullable. So these might have a prefix parser, might have an infix parser, and has a precedence. Gosh, I should look that up. How to actually say that. I read it often, but I don't really say it much. And we're gonna have a little dispatch function that we call on, like, hey Brian. I was watching Brian's stream earlier today, which is really good. I'm not sure, was that the first time you were doing a live stream, Brian? I'm not sure. Anyway, I think it was, and it was really good. So I'm using the same software I think that you use. So let's just, you know, pray to the bytes that it doesn't crash on me or on us. Okay, so we don't have this. Let's see, where should we start? What should we start with? We could start with let's skip the function thing for now. That's kind of complicated. Let's start with like a register. Yeah, so one of these. So when we get one of these tokens, it's going to be a prefix thing. So when we get one of these tokens, we want to do, let's see here, the signature for so it's a prefix one again, right? This looks like this. P state here is P. This is just a local function. So let's call this parse reg, right? And here, P toke equals ireg. And then we're gonna somehow produce a node. And for now, let's start with this stepping out. This node definition here, struct node. Let's do compile quiet, and then static const node, like an invalid node that we can just return for now. Let's see, scroll this down a little bit. This node, it's gonna have that be 0. Okay, bad. And it's total Wild West for me here. Just const cast here. And this is angry because it's the wrong function. So we're gonna have our pureg function here. Yes, we should do this to be good, good C people, but like the compiler will figure out. No, that's really the only way to do it, I think. A complain? No. Excellent. And this is sort of the precedence. We have to think about that for now. Now, this is essentially going to be important later for, you know, if you have things like, you know, x plus y times y plus c, like which of these gets an implicit parentheses around them, right? In C, it's this, so multiplication has a higher precedence than addition, for example. I mean, those rules are like the source of much confusion, especially for someone new to programming language, or definitely someone new to programming in general. I think it's generally it's not good to have those things, but for some things it's a necessity. For example, if we have a variable and we do equals, then equals should have a higher precedence than multiplication, right? Since we're not doing k equals x and then multiply the result of that, we're doing, you know, x multiplied by y and then this, right? I know. So that's what the precedence stuff is for. We're gonna have very minimal amount of that, if any. I think maybe a little bit. Equals this. Okay, so that works. The compiler is complaining up here and saying, you know, that we're not making use of this. So let's do that. So again, I'm looking at my CO one. So parse prefix. I'm just gonna, okay, let's do this. So the signature of all these parse functions are going to be roughly the same. Or actually, I wonder if we can make them the same. We can use tail calls. That'd be nice. Bye-bye, Brian. Okay, so P statement. So sort of like parse like anything. So the first thing we're going to do is to grab a parset from the table. So this is where the sort of the magic happens. So, oops. Can't use P twice, but no big deal. So we're going to grab just the address of whatever is the current token. And then for now, we can just try and say, let's log a little information. So we're going to have token name of the current token, and then just let's log just the address of this. We just have one of them now, so we're gonna get this null here if we're encountering a token that's not alright. And let's see here. So if we did not find a parselet, we should log, that should really be an error. So we're not going to do a penny guess now, since like in the beginning we are slowly building this out. So instead, let's just log the fact that, you know, we're missing parselets for the token. Oopsies. And let's just return. Oh, dlog is no, we can't do that. So return k bad, right? So we got a bad result. Doing this instead of returning null has like some really useful side effects. Maybe we can talk about it later, but doing this is just, I find it at least to be generally more flexible than returning null as a condition when something fails. For example, it allows us to just keep parsing. We'll still have like a valid AST. So now we did get a parset, and if this doesn't have a prefix, so if it doesn't have a prefix function, so no prefix function, we essentially have a similar condition, but we're just going to use a different little message. So no prefix parselet for the token we parsed. Otherwise, what we're going to do is return. Now we're going to just transfer control here to our parselet, the prefix function. That's the parse state. And of course, I made a bunch of errors. So let's see what I screwed up. So this is a very verbose. It's probably just one issue. Token name. Oh, yeah. So I've defined it further down. So that was a mistake. So what we should do here, I think, is just to move our parse code to the bottom, since we can just jump back and forth. I'm going to use an editor function here where I can make little bookmarks. So down here we have our main parse function. We have a little debug, printing thing. Then above here are the scanning functions. So main parse function. And above here we have the scanning stuff, the stuff that makes tokens. So it kind of roughly follows the order of, you know, what the assembler does here, right? So first comes all the type defs and stuff there, but then comes the functions for tokenizing stuff, then comes functions for parsing, and eventually we'll get to functions for analysis and code generation. So we'll do that in order, and it'll be easier to navigate our source file. Okay. So here we have parse register. We have the table we're building up, and our, actually we can just, no, we might need a separate function later, so we gotta keep this here. Here we have our dispatch table, and here we have sort of our generic, like, root parselet, essentially. Hello, Henry. So parse any statement. Let me scroll this down. Okay, so let's build this. It works fine. First thing we do, we're not using any of this yet, so let's just like add this to our code path. So here, this is where we have a loop here where we read a token at a time. This is the output we're seeing here, right? So we get a keyword function, sort of a keyword function, a symbol that is the name of it, and so on. This is where we're gonna parse. Let's see. Actually, no. Let's wrap it around. So what we're gonna do is this. Call this file. Let's just call this file for now. The translation unit, whatever. This is gonna be the whole thing that we parse. Is this the best way to do it? Let's see. What did I do with CO? Interesting. I'll just since I'm looking at this, my screen is pretty big. I'm just broadcasting part of it so that the text isn't too small. So I'm just looking outside of it. That's why you can't see it. So this is the parse loop that I use for CO, and I think I'm gonna do pretty much the same thing here. So that, you know, the scanner and stuff works a little differently, but conceptually it's gonna be roughly the same. So yeah, we still have a loop, but instead of doing this, we're gonna do all ptoke not equals, actually we're gonna have to do this. Well, we can use this. We're gonna have to get the first token. Yeah, that's what we gotta do. So lead with a scan token statement, just to sort of prime the our token scanner, so that at this point before here it's sort of invalid its state. We haven't even started looking at the input source, and at this point, after calling that, we will now have set up piece fields to represent the first token, and that's where we enter our parser. And so we'll place this little logging function we have, that's printing things out on the right side here. We might actually, it might be easier for us at this point to move this log function into the scantoke function, since we'll be calling that. Otherwise we won't be seeing. Let's see. Actually, let's do a nasty little trick here. So I don't want to edit this as multiple return, conditions. So kids, don't try this at home, but yeah. Did I call this p scantoke? Scantoke. And then this expects to get the token. Yeah, so this is like, you probably shouldn't, this is just a cause for many bugs, but I'm just gonna do it for now, just to get started, or at least for debugging. So this shadows this symbol with a preprocessor macro. So like wherever beyond this point, so it's position dependent, right? And so beyond this point, wherever this happens, we'll actually get this. But then when we expand this, it's not like it's infinitely expansion stuff. So it kind of works, but it is it's tricky. So do scan toke. So now it's going to print whatever we call scan toke here. It's just going to print our logging function, which we now have to declare. It's further up here somewhere. Since the parse functions, we're gonna need to access it. Actually, we can just put it above our parse functions, which is here. Nice. Then let me make a bookmark on this thing too, like here. So now we can between the type defs and the main statement parser. So let's see what errors I have. Oh, I pasted this random code in here. Just gonna paste it in a random spot. That's okay. Just keep it around and get syntax highlighting. Sometimes you just do this. Now you know this is not defined, so we'll just compile it, just ignore these lines. So that is not the file anymore. So this is just the node that we parsed, and so parse. Oh my god, if I can spell. Parse the node. Yay! And maybe the memory of that, or the address of that. And so of course it's incorrect. Now loop forever, since we're not calling scantoke in the p statement function. So let's go and do that. Oh. There we go. It's the little bash script trying to kill that didn't work. So I'm just trying to figure out to structure this in a way that makes the code small and readable and not too crazy. Again, we're not going for like performance or anything like that here. Okay, so because this is not where we want to do our scanning or of the next token. Rather, also that's incorrect. So we want to put that in here and consume. Logically speaking, this is kind of what we're doing. So consume the treg token that we just received. And in the case that this happens, we have to make some progress to not get into an infinite loop. Okay. So kind of works. Well, I wouldn't call it a works, but it does not explode. Let's see. So let's first start by just commenting out some things here just to reduce the input and the noise a little bit. So for example, comments, we're gonna get some comments here. For now, we're just gonna ignore those. So let's make p like ignore maybe, which does like consume token, right? And a token, it just returns like the, you know, invalid thing. Use comment. Okay. So now we'll silence those things. Parse node, yay. So this, let me see, this is the address that we were given for the bad node. NK and bad, I don't know. Usually, it's old habits die hard, you know, like tend to call things like lowercase k, uppercase, and it's even so established that the editor here has special syntax for it. This is sort of like a tradition, at least on Mac, to do lowercase k, uppercase some letter for constants. But yeah, let's just stick with it now. It's kind of, it's just like awkward for a small program like this. Just call it like bad node. Bad node. Keep it a bad node. Okay, back to our step parser. So that's what we're seeing there. And now when we parse the register, it's a prefix. We want to generate a node for that. So for now, let's just silence some of this logging since it's so noisy. And let's silence these. We know that there's none for these for now. Oh, yeah, this of course will never be null. Let's see, what is the best way? Let's go. So we're not making use of infix parsers yet, but we'll do that later, I think. Okay. So now we can focus on parsing this. So first off, we're gonna want to allocate a node, and now we're gonna have to pass in our memory allocator here, so we can allocate some nodes. So rmem, and this one we can stick that. We can pass that. Should we pass that arguments? Or stick it into the state? I mean, we're gonna need it like pretty much everywhere. So let's just make an argument. And let's grab a page from an old book. So we want our parse functions to have the same signature, at least most of them. Oops. So the parameters are rmm, a pointer to an allocator, and then p state, which is our current parse state, and then for args, parameters takes, and then when you forwards to another call, these are the arguments that are expected. And we can actually lift these up. We want to lift these up all the way up to our parse loop definition up here. I wonder if it should, no. So yeah, here, this signature is going to be different. So, you know, That's what it is. Oh, yeah, of course. So now we can do RMM. So alloc Z maybe. We get that right? Yeah. We have our memory arguments and params here that we're passing along, and size of node. And the alloc Z function gives back just zeroed memory, so this is going to be zero initialized. Now we can return the node. Oops. Oh yeah, of course. We need to go back where we are calling our function here. Yes, we have to pass along the memory, the allocator. Okay. Let's say this one. Too many arguments. Function call expected. No, what? No, mistakes. Really? Oh shoot. Didn't update the definition. There we go. Okay. So parsing a hood. Oh, got a bug here or something? Or did I? Yeah, I erased that. Oh, that's great. So this would be a good sample to start with. Okay, so you receive get a different address. So that's the node, the AST node that we parsed here. And if it's going to be an AST, or we just go straight to like SSA graph, like I'm not sure. It might just be cheaper to just skip the AST stage, since this assembly is pretty simple. But node or value or whatever we're going to call it, we can just rename it later. So now we're going to need a way to just store information about the nodes that we parse, right? And we're going to just sort of stick them together later. So go to our node definition here. We can replace this placeholder field now with a type of node. And since our tokens are, here's a list of tokens. Since our tokens are almost, that might just be enough as the type, sort of type of node thing. We can probably just use that. So we call that rtoke. Is that the name of it? Yeah. Type. And we're gonna have a union, so sort of like different fields depending on what's in there. 64 for an integer value. So a register is gonna use this, for example, or like a a numeric literal. We might want to have other things here, but this we're gonna need this for now. It's gonna be enough. Okay, so down to our parse register function. Let's do a bookmark here. So I want to say type of this is tireg. I guess what we could do, if we wanted to simplify this, we could just do, if we wanted to use this for both floating point registers and integer registers. So we can do this. Now we can take the token of the parse state before we advance it to the next one. We might also want to save the source location of a node. We gotta get these bookmarks. So we can do, oops, line and column, source line and column. there's some neat ways to accelerate this with lookup tables and stuff if you want to make this like efficient, which an industrial strength compiler would probably not save line and column for every single node, but more of a something smaller that goes into a table and you go and do the lookup just when you actually need it, because in most cases you don't need this information. But again, we're going for simplicity, so let's just stuff line and column in there. The next we're gonna do line is the line number, and then we have the column, which is derived. OP column. Okay, so now we have line and column. As we're parsing these things, these tokens here, we could, let's see, let's go down here. Add the location. So we see that works. Line and column. Gonna be 0 for all the bad nodes. If we get them, yep. So we're gonna use a 0 for bad nodes here. So maybe you should take a second there to just have a look at this, see what's going on. So these lines that look like this, they come from our log function that's right here. This, the logs the parse state. So it's gonna going to log the essentially the token, the source location, the token symbol that we use from the enum, the string value in the source text that made this token, you know, and optionally some the value both in decimal and hexadecimal for things that are integer. So like, you know, the equal sign does not have a value, so it's something. And then this, which he has added now, it's down here, will be the output for a node that might be one or more tokens. And so this one didn't produce a node because we don't have any parselet defined for the equals node, right? So we just skip that. And for now, if we re-enable this like little log message we have over here, we're gonna see that it'll say no prefix parselet for t equals. So in this case, we'll skip it. We advance to the next, we skip that token, and we return the bad node. And actually, let's just keep that no message on. So we're gonna get for semi and we get for t equal. Okay. So let's do the equals next. So this is good because this is an infix parselet. So I'm just gonna copy this. So this is equals, maybe call it infix just to make it clear what it is. And we're going to jump up here. And infix parselet takes a couple of extra parameters. Gosh, I wonder if this could be simplified. Well, let's just do this first off. I'm not sure we need the precedence data, node left. So the reason why I'm trying to make these parameters the same is to make sure we use tail recursion. It's mostly just, you know, because it's like fun, nice, slash, you know, cool, whatever. Or cool, I'm not sure if it's cool, but it's nice. So let's do params infix. Almost there. Since again, our first take here is probably going to be wrong, and so it's good to use this little macros here, so it's easier to edit our code later and play around with stuff. Right, so pargs and left. I'm going to pass it along. I don't think I'll ever need to do this, so let's just leave this for now. Params infix. Let's go down to, oops. So I'll do that, set the bookmark here. So perhaps infix. And now, oopsies. Did I just do, oh, I should change my keyboard bindings too, and I'll do that. I do that actually, I'll click that then. Now we're gonna add new entry for the equals token here. And now we're gonna leave, the prefix parser null because we don't have any for equals, and we probably will never have. So again, prefix parser is when something, essentially when a line begins with a token, right? So if there's token A, B, and C, right? An prefix parser will only be triggered for a token that's at the beginning of a statement. An infix parser will only be triggered for a token that follows a, logically speaking, a something else, right? So it might get invoked for this, it might get invoked for this, depending on how many tokens are consumed by prefix parser. So for equals one, we're gonna have our equals infix parser in here. And now we're not making use of that, right? Since there's in our statement sort of root parse function here, we're never making use of the infix parser. So let's change that. So how this works is we take, first off, we can just do this. So if ps infix is null, we can just immediately return. Otherwise, what we're going to do is take the left value and let's see, I have to think for a second here. And let me actually look at the SEO parser. Okay, so I think what we might want to do is to separate these into two stages. Okay, let's just do this. So now we have the left node here, and then infix time. So infix time. I'm gonna do now we have to do a new lookup here, since this might have changed, right? Since the prefix, the prefix parser must have had, and you know, we could add an assertion here if we wanted to. It must have had advanced the token. Actually, let's just do that. Just make sure we're not making mistakes. So used, this is just to silence the compiler layer, but used rtoke t1 p toke. Actually, we can just check the make sure is that we advance the input. And assert that these are not the same, right? Rather than parser is less, so that this had been advanced. And yes, that we would trigger this parse left. Not advance scanner. Otherwise, now we know that we will not get into an infinite loop here. Oh, is it unused? Oh, I suppose. Oh, and that's constant. So it's angry. And then there's some other warnings here. Oh, yeah, okay, whatever. We never go in the other direction anyways. I think. Oh, you never know. You might do something stupid. Or you and pointer. Oh, we're not using that yet, and we're not returning from it. Okay, that's good. The next thing that we do is to do a lookup again. So now we have a new token. So we're going to look at this up, and if we find a... So let's see, we're going to have the loop here. So while our input stream is valid, while toke is not our T end token, we're just gonna keep doing this. So we're gonna have to do this loop for infix operation so that when we have something like this, it's Y, it's a couple times Z, K, then what will happen is that this will trigger a prefix parselet, so this becomes left. And then, below this makes sense. And then this is gonna trigger for an infix parselet here for multiply, right? So we're gonna then call an infix one with this and left. And that in turn is going to trigger the prefix parselet for this, for Y. And that will trigger the infix parselet for this. And we'll do this one more time for Z. I realize it's too many to illustrate this example. Left for Z. And I'll treat another one. So that'll be the end of it. Right. So this is roughly what it is. And what we expect to get out of this as some sort of AST thing is if we go from the bottom up, right? We're going to get Z multiplied by this thing on the left, which is Y. It's multiplied by X, right? So structurally, this is what we're going to get. And which order these end up in is going to depend on precedence too, so we're actually going to do that check in here too in this while loop. Okay, so now we're going to grab the parselet for the current token, and at this point, we have to check if this token actually has an infix parselet. So infix. So if it doesn't have one, or we can be explicit here and spell it out null. So if it doesn't have one, we just want to end our loop. And we also want to look at the precedence of this. If it's less than our current precedence, oh gosh, I guess we should add this to our params. It's nice to have this. So it's the current precedence that we're parsing. Okay. So our current precedence is different, so let's see which errors we made now. Just in case it didn't make any. 352. So we definitely did one error there now, which is that we're not passing an argument to do a call, but here PR. Oh, yeah, so didn't update that. And we're still not using left, that's fine. Okay, there we go. 422. can have at this point, we just have which I think is member. I think member is the highest one. Oh yeah, this editor doesn't understand enum values. I couldn't jump to it. I tried to jump to it. Yep, so it's the highest one. And actually we did do a type def for this, so let's use that in our parameters. And do we need these to not? Okay. So this is gonna work, and we're just gonna bail out. And look at that, we were saved by our shik. Is that correct? Actually, I think we did advance things, didn't we? No prefix parselet 4. So we bail there and I parse the node. I'm not. Interesting. What have I done wrong? Definitely done something. Oh. Wait. No. Am I totally wrong here? Okay, let's just do this for now. Okay, what is going on? Let's see, am I crazy? Yeah, I am not crazy. Something. What am I doing here? This should definitely have been advanced by this. Okay. The good old printf debugging, call me out to play. So at this point, that point. Are they different? They really should be. They're not. What the hell? Scanning this. This definitely advances the input cursor. Oh! Okay. We're getting a semicolon, which is it has a 0 space. Is in, it's not real. It's synthetic. So it doesn't advance. It actually it progresses the parser, but it doesn't advance the input cursor. Okay, that's funny. So I guess to actually detect this in the debug thing, I have to save the state too, since okay. Good. At least I know I'm not insane. So we're gonna save the state too. Space those out. So we're gonna make sure that either, let's keep that one line. Yeah, either these are different, or either this changed, or the input cursor changed. Okay, it's gonna be enough. It's gonna work. Okay, back to the infix parser. See, sometimes a little bit of a self what is it called? Sort of to be humble to one's own abilities and toss in a little assertion can go a long way of helping. Would have been just annoying sort of hanging there otherwise. Hey, Coon! Smooth. It is a smooth little thing. Okay. Let's see, it's still working. Okay. And now we're returning something, which is good. Up here, we can actually just like do a return instead, since it's gonna read a little cleaner. And what we're gonna do now is that we want to replace left with the infix thing, right? So if you remember this little explanation of infix parsing here, with the precedence too, what we're doing is like, we're reading a thing, right? It's essentially we're making use of just the stack of the program here. We could implement our own stack if we wanted to, but why bother? And then we keep sort of reading, you know, so we read this and we group these, right? And then this thing reads another token right over here, or another expression over there, which, you know, keeps grouping and stuff like this. And then we pop the stack, so to speak, we come back, and that's just how we'll group things. And we get the ASD we expect. Is kind of elegant. The precedence check here is to make sure that the infix parselet that we're receiving, or that we're about to make use of, has a precedence that is the same or higher than the current precedence. Otherwise, if it's lower, then we just stop there. And that's how we can do things like, so if we take a different example. So let's take an example of plus, right? So we do plus here. So now this has higher precedence than plus. So that means that as we are getting, so I'm going to copy this and going to follow along here. So first up, step 1, you know, these are numbered. I don't know if my editor can generate numbers, but I used to use sequence sometimes on the terminal to do this, but it's a few numbers. Let's type them out. The steps that we're taking. Okay. So for this example, the first step is, you know, we read X, and then we have an infix parselet for the multiplication symbol. So we do that, and we pass that along the X, right, the left one, and then we read another thing, right? So that reads another expression, which is Y, by calling the same function that we're in, so recursively. So it calls P statement again. And this is where the precedence thing is going to kick in. So it calls this with the current precedence of this operator, right? And then it finds a plus operator in this case. And it's not going to call this infix parselet in this case here. So what it's going to do, it's going to return. It's not going to do anything. So it will pop this. So it'll go back. Well, actually, I guess that is step 4. If we wanted to be precise. And at this point, we will call the plus with the left. And so a result is going to look different. So a result is going to look like this. Wait. Oh, I think I messed up here. Oh, this is confusing. I think I made a mistake. Did I make a mistake here? Yeah, I think actually we get the CY. Yeah, that looks more like it. I think that's what we get, XYZ. Sorry about that. That's confusing. And so now, you know, the order of things are going to be different, since at this point when we get here, this is really the key part right here. Is that when we get here, or in between here, the precedence for the plus infix operator is going to be smaller than that of the current one, the multiplication one. So we'll return from this function, which is going to be, this is going to happen. Right? This is going to be true suddenly. The precedence is going to be lower for plus to multiply, and we'll return without calling another infix thing, which means that when we get back here, plus is still the current token, and this thing is going to be triggered on the outer scope, and it's going to wrap things up. Okay, so now at this point, what we need to do, right, is to actually call our infix parselet. Hey code, let's see. So this is running a pseudocode, your way of avoiding breaking your brain when you have to write recursive things. Yes, yes. In a previous video I showed, I think let's see if I can open this file. I think it was this one. So when I was working through the virtual machine, and I had a bug and I didn't realize it, I wrote like a C version of it, and I have my compilist compile it to this, and then I step through, you know, step by step here, because it is a recursive function. So step 2, you know, what is the state of the registers and x86 here? Yeah, that really helps. Yeah, totally worth the try. I think especially for like stuff like this, it's so, I find it so abstract when it comes to the motion of the program here to think about this when all I'm seeing is just this, right? So no, there's better, you know, I would have taken much more time to make this look better and more readable for future me if this wasn't just sort of like a live share thing. But the point is still the same. So we're gonna call this infix parselet here, and we have now we have different arguments. So the arguments do actually change a little bit, and that's fine. We're not going to be able to use tail calls in those places anyway, since you know we kind of do use the stack for a lot of stuff. So let's see, what do we have? Oh, I suppose we just have the args here. That's cool. And then an infix thing takes an extra thing, which is like the current node, the left. We call it left here actually, but we can just call it node since we're just gonna keep wrapping this, wrap it a wrap. And you know, we're not gonna do this now, but like as an optimization, or if you feel inspired by this pattern, like one option here is to have infix parselets return null as a way to say, hey, actually no, I don't want to care for this. So if you have a context aware syntax, you might have something like let's say the equals infix thing that takes this extra node at the end here. Let me just do this instead and get rid of this. Okay. So what you can do, let's say that this will conditionally like eat up the equal sign depending on what left is, right? So let's say that if you get like a number and equals, it does one thing. Let's say you do x and equals, right? Then it wants something here. And if it gets like a numeric literal and equals, it like does nothing. It's almost like an undo. And a really easy way to implement that is to allow infix to return null in that case. It would like it would look at left. If left is not a symbol, then return null. Right? We gotta remove this since we don't need this here, and then down here, in this loop, you can check for that. If n is null, then break. And since if that's true, we have not advanced the parser at all, and the break, or we can just do return n. Right? Let's type it here. We can just do return n. At this point, like the parser is not advanced, we'll return to wherever call this thing, and that thing will eventually call either the root parse statement or some in between parse statement, and it just continues at that token. And then something else can handle that token. You just get all of that for free by doing it that way. It's pretty neat. And another thing we can toss in here just to make sure we're not writing when I have little bugs is that we're just gonna do this for the sake of our test. No, we got node equals node 2. It's that node, we did not just get back the same node. Actually, is that important? It's not important. It's not important, not in our case. So let's just, less code the better, right? So now we're done. And let's keep this comment here for now. So now we're at our equals, equals infix parser here. So now we can just log here. Oh god. We can just log here to just see that this is actually getting called. Hello, hello, hello. With we're just gonna print the rest for now. we don't have any formatter function for nodes right now, so we just print the address. So we're gonna get hello here with this node, right, that we parsed. So that's the R1 node that we created. So what happens, this prefix parselet is called, it allocates a new node, it populates that node's kind of fields, right, with like, you know, it is a ireg or freg. So maybe click one is better. It just remembers the source position for that, and then it consumes that token that it just parsed, right, which is going to be the register token. And then the next thing that happens is that this node that we produce here is passed on to this function, right? So now we get it here. So what we need to do in here is we're doing the same thing. So obviously we could break this out into a helper function. So we're doing the same thing. We're allocating a new node. We're setting the type of that, right? Which is going to be, what's it? Is it equals? Yeah, so it'll be an equals node. And this node is going to have a member that is left, maybe. Let's call them X and Y. So an operand, right? So operand, maybe it's better to do this. So operand left, and equals also want an operand, a second operand, right? So at this point, it might be useful to do this. Equals is, let's see. So come up with a little syntax here. Infix equals equals up 1 and up 2. Actually, it would be an expression, right? And this would be a either a register or a symbol, and on the right side an expression. So that is roughly the pattern by which that we're parsing here, right? So left is going to be our destination, right? And we can just give that a different name. So it's going to be the destination, and the right side will be our source. And we're going to have to parse it separately. So we're going to do node source is p statement, and we p args there. And now we have to pass the precedence along here, right? Actually, we are piping that through. I'm thinking, do I need to pass that through, pipe that through? I think I do. Just looking at some of the code. Wrote for CO. Okay, let's just skip that for now. We'll get to that later. So, first off, this, I guess, is not reachable here, and we need to define the fields. So let's just, these are referencing each other, right? So one has to come before the other. This is going to be referenced by most things, or a lot of things. So let's put that at the top. And eventually we'll get to this. So let's just make it a macro for now. So we can say we actually want to parse an expression. So on the right side, we want an expression specifically, not just any statement, but an expression. And then later on, now we can start doing this and add some extra signal to our program here. And later on, we can improve the quality of things by giving this p expression a dedicated implementation and make sure an issue is an error if what we're parsing is not an expression. But for now, let's keep it simple. Okay, and now we fix that. Now we need to define the operand fields, right, on our type. So we're not really using this anymore. We're kind of here, and we have a bookmark. So let's go here, brand 2, so node So this is going to be used for, it might be useful to decorate these. So this is for any of the register types. There would be more things to use as this field later. This is going to be used by pretty much anything. So we can just do bin op, binary op, binary op, right? Anything that needs one or more operands, one or two operands. Okay. So now that works. That's cool. And at this point, it probably works, but we can't see it since we don't really have a function to visualize what the ASD looks like. So maybe we should do that. Hello, that we just added it in just to prove that we got here. Right. And we actually have a bug here, so I'm going to move this up here, just after the. So at this point, beyond this point, accessing P will be for the next token that will be processing, and would cause issues if we did. And if we move this up, right, we would get the line and column of the next token, not the one that we just parsed. But it's also important for this. So this mutates the state of the parser, right? This advances the parser forward by one token. And actually, maybe we should rename this function to next advance, maybe. P advance. It's maybe a better name. Okay. Because we need to do this before we, parse a new expression. Are we passing along our? Yeah, we are. Okay. I'm just thinking about the person's value. So I don't really care about that now. But this, we're gonna have to change this here later when we do. Since that kind of depend on the specific thing that we're parsing. I believe there might be some nicer way of dealing with that. Yeah, just keep thinking about it. So I'm gonna just remove this and to try to keep this function small so we can keep it on a screen. This, we are not making use of this really. Let me change noise. And now we have this semicolon here, right? So it says no prefix parser for t semicolon, and again, semicolons, like we produce them automatically at the end of a line, depending on what the last thing is on the line. But for most things, we just automatically produce a semicolon there. If the line already ends with a semicolon, we don't. So if we actually explicitly put a semicolon here, we're gonna get the same. So we are supposed to get the same result. We do not, because there is a shortcoming in the scanner. So let's fix that. So the conditional semicolon, or the synthetic semicolon, is it's a nice little thing that I mentioned this before, but it's a nice little thing that I picked up from the Go compiler. It's essentially a way to make it really predictable to where semicolons are automatically inserted to allow you to just write code like this. So no semicolon at the end, you just know that it's going to be right here. And the rules for these should be pretty straightforward. So like anything that is kind of like a beginning of, for example, a start parentheses, or like an operator like this will not cause a semicolon to be inserted, right? Since they expect something to follow. And in the case of, we got the bug here. In the case of semicolon itself, obviously we just got a semicolon, so no semicolon should follow. But for things like a name or an integer literal, it should follow. And so now I might introduce a new bug here by setting this to false. But let's do it. And let's make sure that I actually set this to true. And so I'm sort of like shedding this here. see, is this gonna work? I think actually this is gonna work. Just semicolon. Yeah, I think this. Yeah, so just going here. So this is accidentally just unrelated. It's just checking the state here to make sure we didn't have a prefix parselet that didn't advance the parser. Should maybe, yeah, eventually we'll remove this or do this more elegantly. So I'm just gonna leave this messy like this. Okay. So back to this. So what I was saying, we fixed that little bug now, is that if we leave out a semicolon at the end of a line, and that line ends in this case, you know, a name, we automatically produce one. If we add something like another equal sign here, actually let's do the slash. We are gonna get t slash, but no semicolon at the end. We can insert one explicitly, and we get, you know, now this it's gonna trip our insertion, and we're gonna get a semicolon, of course, if we enter one in source text. But the parser is not gonna synthesize one for us in this case. And of course, you know, we ignore white space, so you can do that too if you want. So now what we need to do is to handle semicolons, and semicolons in this, at least in this little syntax, has not special meaning, but we treat them in a special way. it's the sentinel, it's like the separator, the terminator, it's like the end of a thing, like just as in plain text, you know, carriage like return, or like a line feed character, like a, you know, a line break ends that line, right, and starts a new line. Similarly, in this syntax, a semicolon has the same purpose. A semicolon ends a statement and potentially starts another statement, or separates two statements. So what we do is we say that for these rules that we have, right? So the equal, actually it's like assignment. The assignment rule here expects a semicolon at the end. It's only valid if it ends in a semicolon. There we go. And yeah, that's really all we need to do. And so what we need to do here is to make sure that we get a semicolon at this point. And we can make a helper function of this, but for now we're just gonna do this. Assume token. Gonna make sure that we get a let's just make this help function right now, because it's gonna make more sense. So we want the semi I'll copy this one. And this is going to take p state. What we're going to do here is that we do an error checking, since this is a very common thing to do, to say at this place I want this type of token. We're not going to do advanced in this one. And if we don't get that, we'll issue a syntax error. And that way we don't have to do this over and over in every function that needs this thing, right? So we take our token expect, the token we expect to get. If the token we have is not the token we want, then issue an error. Right, for now, we don't have any error handling. Or do we? No, we do. PRPX unexpected. There's no formatter here, so I can't include the token just yet. But that's a little piece of improvement we could do in the future. Expected token. That's it. And so if we don't get a semicolon, let's try something else. Let's try green. Now it's going to say line 1, column 9, unexpected token. So line 1, column 9, just right here, right? Unexpected token 3. So that works. And then we can have another function call need consume. Want, maybe it's enough. Don't lift the p advance. Oh, what is a good name for does? Since what we want to do, let's just put in here. What we want to do is to consume this semicolon, right? Oh, wait a second. I think, yeah, no, this is right. We want to do this and not advance at this point. And instead, what we're going to do is in the statement parser, we know that every statement, just shorthand, will end in a semicolon, right? So any, really, any node, and semicolon. So we'll do that check here. We'll do it at this point. So this is when we're done parsing stuff. If the token is not a t semi, then we could just, I'm not gonna just look at my CO2 parser here, just make sure or see what I wrote, when that triggers. Yeah, let's just wing it. So let's see, what would be a good error message? So we essentially want to, we want to eat that token at this point, right? So yeah, so unexpected, expect the token, expected. So we have a little bit more information at this point. Right. Okay, this is good. So now we get the same error message. And now if we do get a semicolon here, should work. Cool. So it's important since if we have two of these, right? Then we're going to do this twice. And let's see here. We can have some lovely bug here, maybe. It looks like too. Interesting. Okay. So some little bug here. So this advances things to skip the semicolon. Wait, what? Yeah, that's not right. How is that possible? Token is set to T end. Oh shoot, did this cause issues? No, it didn't. How is that possible? So let's just make sure that, let's just see if we trigger any of these. Let's just token to end. Blah, 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 whatever. That should not happen. Oh, it does down here, but that's where it's expected to happen. So how is this becoming the end token? Where do we ever assign this? Step through. Oh, an error. Oh, I guess we do it on an error. Maybe that's not the best way of dealing with errors then. Excuse me. Let's print the error message. Clearly, this needs some work, some improvements. You see, invalid register. What? Okay. So this is probably the right time actually to print error messages instead of as I'm doing it here at the end here. So we're triggering this error here, right? So we'll skip this. It'll be fine. But somehow, and hold on, did I that? Yeah, okay. Let's just make sure. So I didn't remove that semicolon insertion thing. Let's see, reset. Oh, it is right here. I did reset that. Okay. So why does it think it's invalid? Is this value larger by any chance? No. It's an error from this parse function. Let us use the more detailed error message. Invalid integer literal. What has changed since this worked just moments ago? Something has changed. It's like the state of the input here. Oh, okay. Oops. We got the invalid register 0R1. Oh, interesting. So the input pointer is at the. Just make a mistake over here. Oh, oh, gosh, yeah. This is what we're looking at. This is totally valid. There's no bug. I'm just making mistakes. Okay, so now it's gonna be fun. Oh god. Okay. So we get the semicolon. Personal register. Okay. I think that worked. It's working. So let's go down to a parse function. The statement parse function. Okay. I think I'm gonna wrap this up now by see if we can visualize by formatting and printing out the nodes that we parsed. So to do that, we are going to write a small formatting function for our nodes. And I'm gonna, let's see, it would be nice for these to be co-located, but yeah. Let's put it down. Parse, where should we put this code? We could put it. We don't want to put it in between all the parsing logic, right? So actually, after here's that's good. LSD formatter. Right, and that's what the node looks like. We'll remove that in a moment. So we're gonna use size, and we're gonna use the little pen buffer. Our code will look very similar to this formatting function here. So we're gonna just copy that. The formatting function that let's copy the whole thing. The formatting function we wrote for the actual instructions, the machine instructions. paste that here. So format node. The destination buffer, its capacity. And this is going to be the node, and we set up, we just, configure an append buffer structure here. Then we will format this node. So this is a hook function. We're gonna have to break out the actual implementation of the node formatter itself, which will take this buffer, so a buff, and it will not return any value. For a node, we can set this to s this. Oh, sorry, compiler. And then we're gonna call this, right? Form a node. We're gonna call that. Let's see. Parse node. So now we can improve on this message. It's a little buffer for printing. It doesn't need to be very big. 256 bytes maybe will be enough. Form a node. We don't care about length. Will be zero terminated. Buffer size of the buffer, and then the node. Now I can pass the buffer in here. Parsed. That's true. So now this will be nothing when we run this. Okay, let's now move back to this. So the first thing we want to do is to just add a string. Oops, what am I doing? This, which will be the toke name. Make sure that works. Look out, parsed, and equal node, and equal node. We could use I find S expressions to be really useful for these kinds of things. So kind of Lisp-like stuff, makes it easy to read. So we can do this, and then now what we want to print here is going to depend on the node, right? So some nodes have this, and some nodes have that. So we're gonna have to switch on the node type, right? So if the and also we want to cast this to the enum type, which is our toke. I keep forgetting about that. Yeah. And now why the compiler can tell us about the cases that we haven't implemented yet or cared for. Save some time. Okay. So we know we're getting the equal one, right? That's essentially the assignment node in our little tiny language here. So in case we get the assignment node, we know that it has operands. It has two operands, exactly two operands, and then we just call this function recursively. It's as simple as that. So we call this with, and maybe we want a little bit of space in between to just limit the output. Then we call the this with our first operand, and we do the same with the second operand, and that's the end of that case. Yeah. So now you see here the compiler is smart enough to know that we're not catching a bunch of different tokens in our switch case here. And eventually we do want to catch them all the Pokemons in this switch statement. This is generally a really nice like practice to. So first off, use like kind of generators. I don't know what other people call them, but I call this kind of a generator. That's almost like a for loop thing for enum values that you'll be working on, that you'll be changing a lot, and define them like this. And then secondly, separate the type def for the actual like the storage for these things from the enum. Now, like the compiler I'm using has the ability to to actually use a specific type for an enum. That's what this little macro does here at the end. But it's not really a standard thing. And so like by default, all enum values in here will just be 32-bit integer, signed integer. And for tokens, for example, we just need 256 different values. We're gonna need less than that probably for tokens, right? And so yeah, so at least what I've found to be good practice that is working for me is to, one, use generators for the definitions, and then two, use enums for the symbols of those things, right? Generate those, and then three, use a type def that is not the enum itself for storage. And then optionally four, you can now use this generator to produce a, as we do a token name function. Oops, that is not the definition here, right? And now we just get names for free, and you get all the kind of stuff. We don't have to add new code, and it's just as simple as adding stuff to this. Maybe a better example of why this is useful is like our instruction set. So since we're using this generator here and the other stuff, all we need to do to add a new instruction to our virtual machine is just to add it here. So we can add mul2 here, and now we have a instruction called mul2. The compiler will complain that in here, in our evaluator, in our virtual machine evaluator, we're not taking care of mul2, so we just have to add that statement, and that's it. So adding, changing, renaming an instruction is as simple as just like editing this list, and everything else happens. And there's little impact to legibility, I think. You could even make an argument that it's an improvement. But yeah, I like this style of doing things. That's what we're doing now. Let's get back to where we were. Okay, so we printed this. The next thing I'm going to do is to handle a iReg. So we're going to get a iReg node. And this one makes use of the ival field up here. So we want to, again, do this, a little space, and then we want to do, now I have to look this up. Is this right? Yeah, it is. Okay, and it takes the base as this. That's the last argument. Okay, so base 10 will be fine. It's again just for formatting, right? So also iReg is it's always on, it's always in base 10. So it doesn't matter. For things like literals and stuff, there are different tokens for signed and maybe signed, definitely not negative. Literals, it's tricky, that one, but we don't have to worry about that. So ival. And yeah, now the ival number seems to be wrong. Oh, it's because we're not saving that when we're parsing. So look, the formatter is already helping us catching mistakes. So when we're parsing this, we have to set up this to and we have to do that here. We have to save that state. And there we go. So now we have, look at what we parsed here. Because now we're done. So we're getting, let's bring in, to summarize this, bring in the source code that we're parsing into view here. So let's use something more interesting just to get a more interesting output. So this is the code that we're parsing right here. So R1 equals R0, which is semantically an assignment. And down we have a second statement, which is another assignment statement, which is we assign register 3 to register 2. And then let's look at what we're parsing. First, as we scan the source, we're getting a register token register 1. Then we get the equality operator. Then we get another register is 0. Then we get a synthetic semicolon from the line ending here with a name at the end. Then we get a register 2. And we get an equal operator, register 3, and a synthetic semicolon. And then this marks the end of our input stream. And as we're going through here, the parser is sort of like lagging behind, one token behind. So that's why we're seeing print out here, which we kind of expect to be behind this line. So you can just ignore that for now. So we're parsing this. which we'll start by parsing this thing, and then we have our infix parselet that we wrote for the equals. So that is triggered, and then that goes and parses the next thing, which is the register 0, and then wraps that up, right? And then this happens once again for register 2. We say register 2 equals 3, wraps that up, and now we have a nice little AST here. Cool. So that's it for this little session. This is probably a really long one. Oh, hey, Kuhn again. Oh, I'm surprised you're still around. Yeah, I know it must be real late over there. Thanks for listening in. Yeah, so that's it. The next thing we're gonna work on in the next part is to make use of this and primarily expand this to cover our factorial example function, to cover all the cases in it. And after that, we'll move on to analysis of this ASD that we're building, and eventually we'll just generate code. And after we're done with generating code, we'll be back to where we were essentially in terms of functionality of having our virtual machine instructions that we can then run through our evaluator or interpreter. But a big difference at that point will be we can just throw in little pieces of text to our program as it's running at runtime and have it just run that dynamically. We don't have to, change our implementation here and compile it and stuff like that. We can just run it. And at that point, I think will be the second big milestone. The first big milestone was when we got the virtual machine to fully function and actually execute a function for us and return the correct result. And the second big milestone is going to be it's going to be a little program where you can give it essentially a script file, right? And you can have it just run that script file, and that's gonna happen soon. So yeah, thanks for watching, and I will see you soon again.